Now we're going to go back to quantum error correcting codes. And in this lecture, we're going to do a quantum version of the repetition code. So 0 goes to 0, 0, 0. 1 goes to 1, 1, 1. Well, let's try to quantize it. Or quantize it, or 0 goes to 0, 0, 0. 1 goes to 1, 1, 1. And I can write a circuit diagram for that. So what happens? So you already know that this is not quantum cloning because quantum cloning is impossible. So alpha 0 plus beta 1 goes to alpha 0, 0, 0 plus beta 1, 1, 1. So can we correct errors? Well, first, let's try to correct bit errors. So what did this channel do? It corrected one bit error. Or not channel. What did that code do? It corrected one bit error. So if you flip one bit, you can get it back. So let's start out by trying sigma z errors, or sigma x errors. Sigma x. Well, we have 3 bits. We can apply sigma x on it. Psi. And so let's apply a sigma x error to the encoded psi on the second bit. So psi encoded is equal to what? It's equal to alpha 0, 1, 0 plus beta 1, 0, 1 plus beta 1, 0, 1. So can we correct this? Well, you can correct it, measure which bit is different. Now, you would like to measure which bit is different without measuring all 3 of these bits, because if you measure all 3 of these bits, you put a superposition into the code, alpha 0 plus beta 1. We'd like the same superposition to come out of the code after you've decoded it. So how do you measure which is different? Well, actually, that's pretty easy. So here's our encoded psi. Well, psi encoded. And we apply a control knot from the first bit to the second bit, a control knot from the first bit to the third bit. Back here, we apply a control knot from the first to the second, and a control knot to the first to the third. You get 0. You get a So 0, 0, alpha 0, 0, 0 plus beta 1, 1, 1 goes to alpha 0, 0, 0 plus beta 1, 0, 0. And you measure 2 zeros. So that's good. And you can see that this decoding circuit is really the inverse of the encoding circuit. So that's very good. And now, what do we have here? Sigma x. what happens if you made an error there? Alpha, so suppose you put alpha 0, 1, 0 plus beta 1, 0, 1 into that circuit. Psi error maybe equals that. When you put it into that circuit, you get out alpha 0, 1, 0 plus beta 1, 1, 0. Because you're doing a control not from this guy to this guy and from the first guy to the third guy. And you measure 1, 0. And your state is alpha 0 plus beta 1. Because this is equal to alpha 0 plus beta 1 times 1, 0. And you're measuring these guys. So what you measure tells you that your second bit is wrong, and you've recovered the first bit. So suppose you put in alpha 1, 0, 0 plus beta 0, 1, 1. So that's our error state. So we got this by applying sigma x to the first qubit. After circuit, you get alpha 1, 1, 1 plus beta 0, 1, 1 is equal to alpha 1 plus beta 0 times 1, 1. And of course, you measure 1, 1. So what do you need to do to the state to fix it? Yeah?
Apply Z.
Apply X. Apply X. So if these are both 1s, if these measurement results are both 1s, you apply X here. And maybe I should draw classical stuff in green. So that's how you decode the qubit code. But of course, not everything is a sigma x error. There's also sigma z errors. So what happens if we apply a sigma z error to this code? Well, there are 3 things you can apply the sigma z to. The first, second, or third qubit. What do we get? Well, here we get alpha 0, 0, 0 minus beta 1, 1, 1. Here we get alpha 0, 0, 0 minus, well, it's the same thing, right? And here we get the same thing again. And all of these are encoded alpha 0 minus beta 1. So what have we done? Well, so we'll call this the bit error correcting code, 3 qubit bit error correction. Well, if you have a sigma x corrected, and if you have a sigma z, you've applied sigma z to the encoded qubit.